Consider R on set A equal to 1, 2, 3, 4, where R is, so what is R on a set A? A relation between two sets, say A, B, is nothing but a subset of their cross product. When you cross A and B, A cross B, you will get all possible ordered pairs. A subset of that is a relation. In this case, we have only one set. So a relation on a set is the cross product of the set with itself, a subset of the cross product of the set with itself. So R is a subset of A cross A. So we are taking one particular subset, and that is 1, 1, 1, 2, 2, 2, 2, 1, 3, 3, and 4, 4. Okay, so find whether R is an equivalence relation. So can you tell me, think and tell me whether this is an equivalence relation or not? No? Why? First property, reflexive. How is it violated? What? Think for a minute and tell me. It is an equivalence relation?
It's an equivalence relation.
Any other answers? So how many think it is an equivalence relation? How many think it is not an equivalence relation? So how many of you don't think anything at all? At least that you should raise hand. No, you should fall in one of these three brackets. What about the remaining? Those who didn't raise hands for either of the options. Okay. So it is an equivalence relation. Why? First condition, reflexive. For all x belonging to A, XRX should be true. Okay. In this case, for all the four elements, each of those four elements, XRX is true. You have 1, 1, 2, 2, 3, 3, and 4, 4. If any one of these is missing, then it is not reflexive. If any one of these four pairs is missing, then it is not reflexive. Okay. Second thing, symmetric. Symmetric does not mean that every possible symmetric pair should be there. Symmetric only means if at all there is xy, then yx should also be there. In this case, 1, 2 is there, so 2, 1 is there. Or the other way around, 2, 1 is there, so 1, 2 is also there. Okay, that's all. You need not again worry about 1, 3, 3, 1, 2, 3, 3, 2. All those things need not be present. Only for reflexive, for each element in A, x or x should be true. But for symmetric, if x or y is there, then y or x should also be there. That's all. And for transitive, if x or y is there and y or z is there, then x or z should be there. You take any possible combination, you will get 1, 1, 1, 2, you get 1, 2. 1, 2, 2, 1, you have 1, 1. 2, 1, 1, 2, you have 2, 2. 2 1 1 1, you have 2 1. 2 2 2 1, you have 2 1. 2 1 or 2 2. Yeah, so we got all possibilities. Okay. And anyway, 3 and 4 don't come in picture because they are standalone pairs. That's all. Okay. So let's write that. R is an equivalence relation because it satisfies all the three conditions of being and transitive. Okay. So first, reflexive because it has 1 1, 2 2, 3 3, and 4 4. Symmetric because it has 1 2 and 2 1. It has 1 1 and 1 2, implying 1 2 and 1 2 and 2 2, implying 1 2, implying 1 1. Okay. And then 2 1 and 1 1, implying 2 1, 2 1 and 1 2, implying 2 2, then 2 2 and 1 1, implying 2 1. Any other case? So if this is xy and this is yz, then this is xz. Sorry, this is 2 1. 2 2 and 2 1 implies 2 1. Okay. Any other case? That's it. So this is an equivalence relation. All right. Any doubts? So even if I don't stop in between, if you have a doubt, feel free to stop me. Okay. Okay. So let's move on to the next topic, that is graphs. All right. So as you all know, there are two kinds of graphs, undirected graphs and directed graphs. Usually whenever we refer to just a graph, it means an undirected graph. Unless explicitly stated, it is an undirected graph whenever we use the word graph. Okay. Directed graph or just graph. It is a set of points with lines connecting some of the points. Points are called nodes or vertices. Lines are called edges. Right? Let's move on to the next page. So if you take and imagine there is an edge between all three. There are edges between all the three, and there can be a self loop on any of the vertices. Let's say V1 has a self loop on itself. Okay, so let's call this graph G1. All right. So next definition is degree of a node. So what is the degree of a node? Number of edges connected to a node. That's all. In an undirected graph, no two nodes can be connected by more than one edge. So if you consider this case, in this case, every pair of nodes has an edge between them. Okay. So suppose if I want to add one more edge between say V1 and V3, that is not possible because there is already an edge between them, and it doesn't make sense to have more than one edge between two nodes in an undirected graph. If it is a directed graph, it is possible because you can have one edge from V1 to V3 and another edge from V3 to V1. That's all. Again, no more than that. Okay. In an undirected graph, you cannot have no two nodes. You cannot have two nodes being connected more than one edge. Okay. But a self loop can be allowed on any given node. So that's why this is possible. Like V1 can have a self loop on itself. You can have it on V2, V3, doesn't matter. In this case, I just took one self loop just as an example. Okay. In an undirected graph G, the pairs Ij and Ji represent the same edge. Right? Since there is no direction, ij and ji represent the same edge. So you can represent that edge either as ij or ji. Anything is fine. So an edge in an undirected graph is represented using set theoretic notation as I comma j as an unordered pair. You remember we discussed difference between sequence and sets. In a sequence, order matters, whereas in a set, order does not matter. In a sequence, number of times an element appears matters, whereas in a set, it does not matter. In this case, order is the differentiating factor. Ij and ji, since their order does not matter, you can represent edges in an undirected graph as a set. Okay? Anything is fine. Usually, we still use sequence or a tuple notation, although it is an undirected graph, because we are used to, that became a convention, that's all. Technically, anything is fine. Okay. Formally, an undirected graph G is represented as an ordered pair of vertices and edges. You see, G is an ordered pair, okay? Whereas the edges in G, they need not be ordered pairs. G is an ordered pair because any graph is composed of nodes and edges, okay? So we should list both nodes and edges. This order we should know so that we know whether the first set, are we looking at nodes or are we looking at edges, okay? So first set is set of vertices. First element in this ordered pair is set of vertices. And the second element in this ordered pair is set of edges. All right. These two are sets, and these two sets constitute the ordered pair, which we call as the graph G. Okay. So any graph is represented as an ordered pair of set of vertices followed by set of edges. Okay. So if you look at this particular example G1, it is an ordered pair of set of vertices and set of edges, right? So what are the vertices in this graph? What are the vertices? V1, V2, V3, right? So there are only 3 vertices. So those go into the first set. And what are the edges? So let's go node by node. For V1, what are the edges? V1 is connected with itself. So V1, V1, then V1, V2, then V1, V3. All right. So let me write that. V1, 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 V2, and V1, V3. Then what about node 2, V2? It is connected with V1 and V3. But V2, V1 should we write again? No need, because we already wrote V1, V2. So that is covered there. So the new edge is V2, V3. What about V3? It is connected to V1 and V2. So normally we should write V3, V1 and V3, V2, but those are already covered in V1, V3 and V2, V3. So nothing new. That's it. So we are done. All right. So this is the list of nodes and edges. And the same thing we can also represent the edges using set theoretic notation. So let me mention that as well. So all that I need to do is I modify these. As sets. Okay, you can either represent like this or like this. Anything is fine. All right. Okay. Next. What is a subgraph? The graph G is a subgraph of graph H if the nodes of G are a subset and the edges of G are a subset of the edges of H on the corresponding nodes. Okay, so let's take an example. So let's assume this is our graph H. Now I can, sorry, I want to consider this portion as my subgraph G. So these nodes will be part of G and also these edges. It's not necessary that all these three edges should be part of G. Maybe two edges or one edge among these three edges can be part of G, but I just took all the three edges and all the three nodes. Okay, so this is a subgraph of the larger graph. All right. Next, let's look at the definition of a path. A path in a graph is a sequence of nodes connected by edges. Okay. Then what is a simple path? A simple path is a path with no repeating nodes. So a path can be as complex as you want. You can revisit any node and any edge any number of times, whereas in a simple path, you cannot have repeating nodes. All right. So you can have cycles within a path because the path can be as complex as you want, whereas you cannot have a cycles in a simple path. So actually now next definition is that of a cycle. A path is a cycle if it starts and ends in the same node. Okay. So suppose if some cycle starts at A, it comes back to A, but it goes to B, then it's not a cycle. It should start and end at the same node. Okay. This is a path. If it ends at B, not A, this is a path of which there is a cycle as a subpart. All right. Cycle should start and end at the same node. Fine. If it ends at different node, then it's no more a cycle. So now let's look at simple cycle. A simple cycle is a cycle with at least 3 nodes and repeats only the first and last nodes. So you see, we have a path and a simple path. We have a cycle and a simple cycle. So the difference between cycle and simple cycle is cycle also begins and ends at the same node. Simple cycle also begins and ends at the same node. But in a non-simple cycle, you can revisit any node any number of times. Something as simple as suppose uh, I cycle the same set of nodes 2 times. Okay. Suppose I start with A, I visit some nodes, I come back to A. Again, I visit the same nodes and I come back to A. Now, this is not a simple cycle because you have revisited at least one node. Okay. Other than the beginning and ending node, if you revisit any other node, it is not a simple cycle. But this is still a cycle because you are beginning and ending at the same node. Okay. So let's just take an example. You will understand better. So imagine I have a graph. You're coming in now. So imagine I have a graph. Okay, so all right. Now, suppose if I just visit these three nodes, right? This is a simple cycle. Okay. Now, suppose if I start here, now in this case, let's assume this is both the starting point and the ending point. All right. Now, let's take another path. Say this is the starting point and ending point. Now I may choose to go like this, then go like this, and go like this, and now I come back like this, and then I come back to the starting point. Okay. Now actually this is a cycle because the starting and ending node are same, but in between there is a repeating node which is different from the starting and ending node. So this is not a simple cycle. This is a cycle, but not a simple cycle. Okay. So yeah, I hope you got the difference between path and simple path and cycle and simple cycle. All right. So let's stop here. Yes, these are everything is a path. This simple cycle is not even here. Simple cycle is a path. Complex cycle is also a path. But none of them are simple paths, because in a simple path, you should not have any repeating node, not even beginning and ending node. Okay.